In this video, we work another example. We've got x squared times the square root of 6 minus x squared, and we're going to determine the intervals where the function's increasing or decreasing, the intervals where the graph is concave upward or concave downward, and then we'll graph the function and use either the first or second derivative test to find any relative extrema of our function. Now, one of the things that I notice is that we've got a square root in our function. And whenever we have a square root, we have to be careful. We don't want to take the square root of a negative number. So if we take the square root of a negative number, the values of the function will be complex, and we don't want complex values. We only want real values. So the first thing we do is identify the domain, and we'll call this function f of x. We'll say the domain of f is the set of all x values in the real numbers such that this 6 minus x squared, that expression under the radical, is greater than or equal to 0. Because we can only take the square root of a number that's positive or 0 in the real number system. Now, if I solve that for x, I get this. 6 is greater than or equal to x squared. Now, you might be tempted to take the square root of both sides, but I think with something like this, it's helpful to just graph the function. Y equals 6 minus x squared is another one of those upside down parabolas. When x equals 0, y equals 6. And we can see that the y values on the graph are positive whenever we are on this part of the graph, when the graph is above the x-axis. Well, isn't that the definition of positive? Yes, you're right. The y values are positive here and here, like on that entire interval. So we just have to find the x values that cause that to be 0. And those x values are when x equals plus or minus the square root of 6. So that this 6 is greater than or equal to x squared has as its solution set all of the x values between the negative square root of 6 and positive square root of 6. So I'm going to write that down here. So that is our domain. So those are the only x values that we're interested in. Now we want to determine where the function is increasing or decreasing, and that requires computing the derivative, setting that derivative equal to 0 to find the critical values, and then also thinking about where the derivative is undefined, and then placing those numbers on a number line, and then looking at the sign of y prime on each of the intervals defined by those critical values. So let's compute y prime. And that that square root is the same as a 1/2 power. Let's remember, x to the n, or divided by m, is the mth root of x to the n. So when I have a square root of x, we have to be a little bit careful. There's an implied 1 there and an implied 2 there. That's an x to the 1 divided by 2, or 1/2. This number in the denominator corresponds to the index of the root, index of the radical. So this square root can be written as a 1/2 power, and then we're going to use the product rule. I've got a first function here and a second function here. So when we take the derivative of a product, we always get the derivative of the first times the second function undifferentiated, don't do anything to it, plus the derivative of the second function that's going to require the chain rule times the first undifferentiated. Okay, so we're still computing y prime here. And the derivative of x squared is 2x. And then the derivative of this requires a chain rule again. Because we've got this function inside that square root, or that function inside that 1/2 power function, right? So the derivative of some function to the 1/2 power is 1/2 of the original function to the 1/2 minus 1, or 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. and then you evaluate it at the inside function. So you put the inside function back in without doing anything to it. And then you multiply by the derivative of the inside by the chain rule. And that derivative happens to be negative 2x, because the derivative of 6 is 0, and then we're subtracting the derivative of x squared, which is 2x. And then we multiply by an x squared. And then the 1/2 and the 2 reduce. And so we get 2x times 6 minus x squared to the 1/2 power. And then I've got a negative x times x squared is x cubed times a 6 minus x squared to the negative 1/2 power. Now, using our exponent properties again, x to a negative power is 1 over x to the same power but positive. This expression is actually a radical expression in the denominator, or this expression to the positive 1/2 in the denominator. So this is 2x times 6 minus x squared to the 1/2 minus x cubed times 1 divided by 6 minus x squared to the 1/2 power. Now, I can think of that as itself over 1. If we multiply straight across, we would just have this x cubed divided by that. Now, because I'm setting this equal to 0 and I'm solving for x, in order to find the critical values, I need a common denominator. And right now, the two denominators are 1 and then this guy right here. So if we want to get a common denominator, well, the least common denominator is just the one that's not 1. It's that one right there. So we're going to multiply by 6 minus x squared raised to the 1/2 power, all divided by itself. So we're just multiplying by a well-chosen 1. Doesn't change the value of anything, just changes the way we're writing it. And that gives us 2x times the square root of a times the square root of a, essentially, which is the square root of a squared, or just a. So I'm just going to end up with a 6 minus x squared in that numerator, all divided by that denominator, minus the x cubed from that numerator, all divided by that denominator. So they have the same denominator now. I can just do this minus that, all over that 6 minus x squared to the 1/2 power. And if we distribute that 2x, we get 2x times 6 is 12x. 2x times negative x squared is negative 2x cubed. And we're subtracting x cubed. And if I collect like terms, I've got 12x minus 3 times x cubed, all divided by 6 minus x squared raised to the 1/2 power. Now, I want to find those x values where the derivative is 0 or where the derivative is undefined, because we're trying to find critical values. And remember, critical values are those x values that correspond to a 0 derivative, or an x value in the domain where the derivative is undefined. So to do that, we computed y prime. And then we want to set y prime equal to 0 and solve for x. Now it's easier to find the zeros of y prime if we factor it. So I look at the numerator and I see that the 12x and the 3x cubed have a 3x in common. Three x times 4 would give me 12x, and 3x times a negative x squared would give me this negative 3x cubed. And 4 minus x squared is a difference of squares, so I can factor that as well. So I've got 3x times 2 minus x times 2 plus x. Because our a squared is 4, a is 2. Because our x, or b squared is x squared, b is x. And we have this expression in the denominator. If you want, you can write it as the square root now. And so y prime is equal to 0 when, well, this fraction is 0. And this fraction is 0 whenever the numerator is 0 and the denominator is non-zero. So we'll find those values. We'll say y prime is 0 when the numerator, which is 3x times 2 minus x times 2 plus x equals 0. So that means that x equals 0, 2, or negative 2. then of course, at those values, the denominator is non-zero. I'm always checking that as well. And y prime is undefined when that denominator is zero. That's when 6 minus x squared is zero, where x equals plus or minus the square root of 6. And those are actually the endpoints of our domain, because remember our domain was this set of x values. Now, 2 and -2 are both equal to plus and minus the square root of 4. So those actually are in our domain. So our those are our 3 critical values. Well, I guess these are critical values as well, technically, even though they're in the endpoints. And we just list those on a number line and then determine the sign of y prime on each of the intervals defined by those. So we're only interested in y prime on the domain of our function, and that domain is finite. It goes from the negative square root of 6 to the positive square root of 6. We want to list these other 3 critical values on the number line in the correct order. So -2, 0, and 2 will be there approximately on our number line. And y prime is this factor times this factor times this factor divided by that factor. So I'm just going to list those factors below y prime here. I didn't leave myself much space, but that square root is always positive. So we don't have to worry about that. 3x is positive when x is positive, and x is positive on those intervals. It's going to be negative when x is negative on those intervals. And 2 minus x is positive whenever x is greater than, or it's negative whenever x is greater than 2. And so we'll have a negative value here. But then the rest of the time when x is less than 2, we're going to get a positive answer. So we're going to have a positive, positive, and a positive. Now 2 plus x is positive whenever x is greater than -2 on those intervals, and it's going to be negative when x is less than -2. So y prime is a negative times a positive times a negative divided by a positive, which makes it positive on that interval. And then y prime is a product of a negative, a positive, and then divided by a positive. So that's going to give us a negative sign there. It's a positive times a positive times a positive divided by a positive, which makes that positive. And then there's only one negative sign here. So it's going to be a negative divided by a positive, which gives us a negative. With this sign chart, we can determine the intervals where the function is increasing or decreasing. Now we know that these 3 values, -2, 0, and 2, correspond to x values when the derivative is 0. So not only is the function increasing on this interval and decreasing on this interval, we also know that the slope is 0 at these 3 values. So if the function is increasing and then it has a 0 slope and it's decreasing, or if it's decreasing and then it has a 0 slope and then it's increasing, or if it's increasing and it has a 0 slope and then it's decreasing again, then we have a relative max there, a relative min there, and a relative max there. So we've just finished a big portion of our question. We were asked to find the intervals where the function is increasing and decreasing, and we have those. We have to summarize the information on our chart, but we know what those are from reading our chart. And we just use the first derivative test to find relative extrema. So let's summarize all of that now. Somebody, right. The function is increasing on this interval and this interval. The function is decreasing on this interval and this interval. And we have a relative maximum at -2. And our function was x squared times the square root of 6 minus x squared. If I substitute in -2 here, I get 4. And then I've got 6 minus 4 under the radical, which is 2. So I get 4 square roots of 2. So my relative max is 4 times the square root of 2. And that occurs at x equals -2. And then at x equals 0, I have a relative min, f of 0, which I think we can all see that that's going to be 0. I'm taking 0 squared and multiplying it by the square root of 6, which of course gives me a 0. And that occurs at x equals 0. And then we have a relative max at 2. And then because of symmetry, because the function is an x squared times the square root of 6 minus x squared, when I substitute 2, I get the same value that I get when I substitute -2, because I'm squaring the x values in our formula. So we're going to get 4 times the square root of 2 at x equals 2. So that's what we know just using the first derivative test and a sign chart for y prime. Now we also want to create a sign chart for y double prime and find any potential points of inflection. So let's do that. Y double prime is just the derivative with respect to x of y prime. We can call that dy dx. So that's the derivative with respect to x of this expression. Now, we don't want to use the factored form because then we would have to use the product rule when we take the derivative. It's kind of a pain. So I'm going to use this version and use the quotient rule. We've got a 12x minus 3x cubed in our numerator, and we're dividing by 6 minus x squared, all raised to the 1/2 power. And that requires the quotient rule. So the quotient rule says the derivative of a quotient is low d high. The derivative of the top function is the derivative of 12x, which is 12, minus the derivative of 3x cubed. So we're going to have -3 times 3, which is -9, times x to the 1 less power, that's x squared. So that's low d high minus high. Don't forget to put that in parentheses because it has multiple terms. Then d low requires the chain rule. So you've got this inside function, and it's inside that square root function. So the derivative of a function to the 1/2 is 1/2 of that function to the -1/2. We put the inside function back inside, and then we multiply by the derivative of the inside by the chain rule. The derivative of 6 minus x squared is 0 minus 2x, or -2x. And we're taking all of that and dividing by 6 minus x squared to the 1/2 quantity squared. So you're going to get 6 minus x squared in general. But when you've just taken a square root and then you've squared something, you would think that that just gets rid of the square root, but I think we also need that expression to be positive. And actually it's going to be positive because we're on the interval of interest where 6 minus x squared is guaranteed to be positive. We're in the domain. So I would put the absolute value of ours there, but it's not necessary because we're only interested in y double prime on the domain of the function. So let's simplify this everywhere that we can. This 1/2 and that -2, or that 2 reduce, and that negative x can be multiplied by this polynomial here. The negative times the negative will make that positive. And so what we get is this 6 minus x squared to the 1/2 times 12 minus 9x squared. And then here we've got an x times this expression. X times this is 12x squared minus 3x to the 4th. And I've got a 6 minus x squared to the positive 1/2 in the denominator. It's a little bit hard to see. But again, if I have a negative exponent, it's the same as that same thing with a positive exponent, but you put it in the denominator. And then we're taking all of that and dividing by 6 minus x squared. So I actually have a fraction within a fraction. It's a little misleading at first. You might not realize that you do, but it's because of that negative exponent that we have a fraction within a fraction. in order to get rid of that fraction within a fraction, I'm going to multiply by the least common denominator of all of the denominators of the larger fraction. So essentially, or of the smaller fractions. The least common denominator is just that. So we're going to multiply the numerator of this expression by 6 minus x squared to the 1/2. And that's legal as long as we also multiply the denominator of the larger fraction by 6 minus x squared to the 1/2. We're just multiplying by a 1, essentially, a well-chosen 1. And we'll distribute that. All of this is multiplied by that, and then we're adding all of this times that. And then this square root times that square root is just going to give us a 6 minus x squared times the 12x, or 12 minus 9x squared. And then when we multiply these two together, we just end up with the numerator. And then I've got 6 minus x squared to the first times 6 minus x squared to the 1/2. So we add the exponents. And if we distribute, well, 6 times 12 is what? 60 plus 12, 72. And then outer times outer is negative 54x squared. Inner times inner is negative 12x squared. And last times last is 9x to the 4th. And these reduce. And so I have 9x to the 4th minus 3x to the 4th, which is 6x to the 4th, minus 54x squared plus 72, all divided by 6 minus x squared to the 3/2. My goodness. Question is, when is that positive and when is it negative? I have no idea. Well, one thing I do notice is that the 6, the 54, and the 72 have a factor of 6 in common, so I could factor that out. Oh, actually, that is going to factor really nicely. And then this expression is quadratic in form, so it can be factored the same way that we factor quadratic expressions. First times first has to give us x to the 4th, so we're going to have an x squared and an x squared here. And the two numbers that go here are two numbers that satisfy the following. We need those numbers to multiply to give us 8 and add to give us a -9. -1 and -8 will work because -1 plus -8 is -9 and -1 times -8 is +8. So y double prime is equal to this. And we want y double prime to be equal 0. So in order to find those intervals where the function is concave downward or concave upward. So we'll have y double prime equals 0. This should be to the 3/2. When the numerator is 0, so that's when 6 times x squared minus 1 times x squared minus 8 equals 0. And the 6 is never 0. X squared plus 1, or x squared minus 1 can factor to x plus 1, x minus 1. And x squared minus 8 is also, you can think of it as a difference of squares, but this is not a perfect square. So we're going to get x squared minus the square root of 8 and x squared, or x minus the square root of 8 and x plus the square root of 8. And that is satisfied when x equals plus or minus 1 and x equals plus or minus the square root of 8, which is plus or minus 2 root 2. But plus or minus 2 root 2 is actually outside of the domain of our function. Because remember, this was the function that we started with, and its domain was from the negative square root of 6 to positive square root of 6. Square root of 8 is larger than that, so it's going to be outside the interval. So we'll rule these out and we'll say these are not in the domain. So these are the x values that are potential x coordinates of points of inflection. Okay, so now we're going to make a sign chart. And we also say y double prime is undefined. We also always need to think about when it's undefined as well. When the denominator is 0, and that denominator will be 0 when that 6 minus x squared is 0, so that's going to be equal to 0 when x equals plus or minus the square root of 6. So at the endpoints of our interval. So they're not critical values, they're almost like critical values. The numbers on our number line for the sign chart for y double prime are going to be these two numbers and those two numbers. And since the domain ends and begins with these numbers, y double prime is just going to go like this. And we're interested in y double prime sign on the interval from negative square root of 6 to positive square root of 6. And we'll list the numbers 1 and -1 there and there. Now, y double prime is this product, is this times this, all divided by that. 6 is always positive, no matter what x is. And then x squared minus 1, well, we can factor that as x plus 1 times x minus 1. X plus 1 is positive when x is greater than -1. And negative when x is less than -1. X minus 1 is positive when x is greater than 1. And negative when x is less than -1. X squared minus 8 can be factored to x plus the square root of 8 and x minus the square root of 8. So this will be negative whenever x is, or excuse me, it'll be positive whenever x is greater than the square root or the negative square root of 8. So it's going to be positive the whole time, because the negative square root of 8 is outside of this interval. And this will be positive when x is greater than positive square root of 8. So it's going to be positive over here somewhere, but then it's going to be negative outside of that interval. So it's going to be negative on the interval of interest. So this is our numerator. It was 6 times this, times this, times this, times this, all divided by 6 minus x squared to the 3/2 power. We're taking a positive number, we're cubing it, and then we're taking the square root. So that's going to be positive. So y double prime is the product of all of these divided by these positive numbers. So since the negatives cancel in pairs and we've got 3 negatives, y double prime is negative on that interval. Since the negatives cancel in pairs, y double prime is positive there. And since the negatives cancel in pairs and we only have 1 negative, we've got a negative there. So that means the graph is concave upward on the interval from -1 to 1, and concave downward on 2 intervals. On the interval from negative square root of 6 to -1, and the interval from 1 to positive square root of 6. And then since our function is going from concave downward to concave upward, concave downward, through x coordinates that correspond to a 0-second derivative, then at those x values, we have points of inflection. Because our graph is changing from concave upward to concave downward, or vice versa. So 1 and f of 1, and our function f is x squared times the square root of 6 minus x squared. When we substitute in 1 here, we get, well, 6 minus 1 squared is 5. So we're going to have square root of 5 times 1. So our y value is the square root of 5. And then at -1, well, we're squaring it, so we're also going to get a square root of 5. So, and that's a little bit greater than 2, right? A little bit larger than 2, and it is in our domain. So we've got 2 points of inflection. We know where the graph is concave upward and concave downward. We know where the function is increasing and where it's decreasing, and we know where our relative extrema are. With all that information, we should be able to graph our function. We can also create a line chart that summarizes everything we've talked about by listing this -2, 0, and 2 on our interval, as well as -1 and 1 on our interval. Let's do that. So we go from negative square root of 6 to positive square root of 6, looking at -2, -1, 0, 1, and 2. And y prime is, are the functions increasing on the interval from negative square root of 6 to -2, so y prime is positive there. And then from -2 to 0, it's decreasing. Then from 0 to 2, the function's increasing again, so y prime is positive. And then from 2 to square root of 6, it's decreasing. And then for y double prime, from square root of negative, or the negative square root of 6 to -1, y double prime is negative. And then from -1 to 1, y double prime is positive. And then from 1 to square root of 6, y double prime is negative. So now we know it's increasing and concave down, decreasing and concave down, decreasing and concave up, increasing and concave up, increasing and concave down, decreasing and concave down. And again, I like to draw my little graphs here to guide me. This is decreasing and increasing, and the graph is concave upward. And this is increasing and decreasing, and the graph is concave downward. So let's plot some points. We have y equals x squared times the square root of 6 minus x squared. So we can graph all of this without a calculator. I actually would like to know what square root of 6 is. When x equals plus or minus the square root of 6, we get 0. And when x equals 0, we get 0. I'm going to use my calculator to approximate that. Okay, so square root of 6 is 2.45 approximately. When x equals plus or minus square root of 6, this function is 0. So we get a 6 times 0, which is going to give us 0. So square root of 6 is about 2.4-ish. And negative square root of 6 is about 2.4-ish as well. Those are endpoints on our graph. And what else do we know? When x equals plus or minus 2, the y values are 4 times the square root of 2. That's another one that I need a calculator for. So f of -2 is 4 times the square root of 2. F of +2 is 4 times the square root of 2, and that's about 5.66. Those are both extrema. I think they're both supposed to be relative maxes from the first derivative test. And f of 0 is 0. That was supposed to be a relative min. So we know we've got the endpoints of our function, the end of its domain on the left and right. And then we have a relative max, a relative min, and a relative max. And we found those using the first derivative test. And then we said, okay, and then we're also interested in the function value at 1 and -1. Those were points of inflection. They correspond to y values of square root of 5, and square root of 5 is about 2.24. So when x equals 1, our y value is 2.24. And when x equals -1, our y value is also 2.24. All right, now let's look at our chart. So on this interval from -√6 to -2, our function is increasing and concave downward. So it's going to look like this. And then from -2 to -1, the function is decreasing and concave downward. So it's going to look like that. And then from -1 to 0, the function's decreasing and concave upwards. It's going to look like that. And then from 0 to 1, it's increasing and concave upwards. So it'll look like that. And then from 1 to 2, it's increasing and concave downward. And then from 2 to √6, it's decreasing and concave downward. So that is our graph. Notice that we found the intervals where it was increasing and decreasing using the first and second derivative and a sign chart. We found points of inflection by looking at where that second derivative changed signs, and we found relative extrema, relative mins and relative maxes by looking at where the first derivative changed signs. Now we can confirm our results for those relative extrema by using the second derivative test. Now we already know that this should be a relative max, that's a relative max, and that's a relative min. But we can confirm that that's true using the second derivative test. So our second derivative was 6x to the 4th minus 54x² plus 72, all divided by 6 minus x² to the 3/2 power. And we factored that to this expression. Now, we know that y prime of 2 is 0. Question is, what is y double prime of 2? What is the sign of y double prime of 2? Well, y double prime at 2 is 6 times 2², which is 4, minus 1, which is 3. And then I've got 4 minus 8, which is -4, all divided by 6 minus 4, which is 2 to the 2/3 power. So this is negative. I don't even have to do the arithmetic to know that it's negative. This is less than 0. Since it's less than 0, that means, since the second derivative is less than 0, that means our graph is concave downward. So we're at a point where the derivative is 0 and the second derivative is negative. So we must have a relative max. By the second derivative test. And if we look at it, y of 2 or f of 2 are the same thing. Well, we do have a relative max there. And we can, if we substitute x equals 2 into the original function, we get that 4 times the square root of 2. If we evaluate the second derivative at -2, because the x's are squared everywhere, we're going to get the same value for this. It's just a number, and it happens to be a negative number. It's negative. So the graph is concave down, but we're at a point where the first derivative is 0. So we must be at the top at our relative max. So y of -2 is a relative max by the second derivative test as well. And that's what we see, and that's what we got when we used the first derivative test. So that's cool. And then y prime of 0 was also 0. We evaluate y double prime at 0. We get 6 times -1 times -8, all divided by 6 to the 3/2 power. Negative times negative is positive. So the second derivative is positive there. And the actual first derivative is 0, so we must be at a relative min by the second derivative test. So you can do this if you want to determine whether those critical values correspond to minima or maxima. Just plug the x value into the second derivative and then use that the sign of the second derivative to determine whether the graph is concave downward or concave upward. If that derivative is negative and the first derivative, if the second derivative is negative and the first derivative is 0, we're at a relative max. If the second derivative is positive, the graph is concave up. And if we're and the first derivative is 0 at the same time, then we're at a relative min. And so that's the second derivative test. And it gives us the same result as the first derivative tested. So let's look at that graph on Desmos.com. We're going to see that we have the same type of picture. Here are our points of inflection. And the extrema are a relative maximum of 4 times the square root of 2 at x equals plus and minus 2, and relative minimum at of 0 at x equals 0. And because we're on a closed interval, this turns out to be an absolute maximum. And we actually have 2 x values that give us that absolute maximum. And the absolute minimum actually occurs there and there and there. We have an absolute minimum of 0 at x equals 0 and plus or minus square root of 6. And it's concave down and concave up, concave down, increasing, decreasing, increasing, decreasing, as we discussed earlier. Okay, so this is the graph on Desmos.com with all the points of interest. I think it is consistent with all of our calculations. The function's increasing and concave downward, and then decreasing and concave downward, then decreasing and concave upward, increasing and concave upward, then increasing and concave downward, and then decreasing and concave downward. These are our 2 points of inflection. I think I did that correctly. Is that right? I thought it was square root of 5. Yeah, it is square root of 5. Okay. So everything is consistent with what we would expect. I've got those points marked. Now we could have analyzed all of this differently by just computing f prime on paper and then looking at the derivative. We say, well, the derivative is 0 at this x value, this x value, and this x value. And we know that those are our 3 critical points. And the function is increasing where f prime is positive. So it's increasing on this interval, decreasing on this interval, and that's consistent with the original graph. Then the derivative is positive here, so the original function is increasing and then decreasing on that last interval, and that's what we see. So that's good. And then f double prime is 0 at these 2 x values. And I think we see that. That's consistent with what we expect. And f double prime is positive from here to here. That's when the original graph should be concave upward, and it is. And f double prime is negative over here and here, and the original graph is concave downward, and it is. And if we wanted to, we could ignore the original graph and sort of ignore all of those points for a moment and analyze f double prime from the perspective of f prime. Because remember, f double prime is the slope of f prime. So f prime looks like this, and it has a 0 derivative here and here. So the second derivative should be 0 there and there. And it is. The second derivative is 0 at that x value and that x value. And f prime is decreasing until it gets to that x value. And so the second derivative should be negative until we get to that x value, and it is. And then f prime is increasing from there to there. And the original, the second derivative should be positive then, and it is. And then when the second derivative is negative, f prime is decreasing. So we do have the expected relationship. That's pretty cool. Our graph online is consistent with the graph that we created on paper. I put the points of inflection in teal, and then our absolute minimums at these 3 locations and absolute maximums at these 2 locations in the same color as the original function. But remember, when you're asked for an absolute max or an absolute min or a relative max or a relative min, you're always talking about the y values. They correspond to a particular x value, but relative minima and maxima are not ordered pairs. They're just single numbers. It's the lowest y value or the highest y value on a list. Or if it's a relative extrema, it's the highest, a relative maximum is the largest y value in a particular neighborhood, and a relative minimum is the largest y value or smallest y value in a particular neighborhood.